Section 4.3, page 2. So now let's talk about the second derivative in terms of the graph, and specifically it references concavity, which we refer to as concave up or concave down. Our graph is considered concave up, which we abbreviate CU, when it has this proper U shape up, that if you thought of it as a U, the arrows would be pointed up. A region of the graph that is considered concave down, CD for abbreviation, is when your U shape is pointed down. And the third thing is these changes occur, going from concave up to down or down to up, at an inflection point, which is abbreviated IP, although I don't actually use it that often. So we need to have a continuous function, and the graph will change concavity when the second derivative is equal to 0. So whichever x causes that second derivative equal to 0. But here's something that's helpful about that information. If the second derivative is greater than 0, meaning it's positive, then that region of the graph is going to be concave up. Versus when the second derivative is less than 0, it's negative, it will occur in a concave down region. Why we care about that is if the second derivative is continuous near a critical number, that means the first derivative is specifically 0, not undefined, and the second derivative is positive, we just said we're in a concave up region. And if you look at this shape, we have a minimum in a concave up region. If you have a first derivative that has a critical number at x equals 0, or c in our case, not undefined, and the second derivative at that exact same point is negative, we know the graph is concave down, but as you can see, concave down means we have a maximum. So actually that might be a faster way to go, but it depends on what's being asked of you. So I'm given another problem to solve, different from the previous one, and I have a whole list of answers to fill in. So whenever I need to find local max and mins, I always need a critical number, and that starts with the derivative. So taking the derivative of the function, I have a largest degree polynomial of 2, so I have a second degree polynomial. I'm expecting 2 different roots. I need to set this equal to 0. Best bet is to always factor the greatest common factor out. Now in this case, once I factor the 6 out, hopefully you're able to factor the trinomial into 2 binomials. As you use the 0 factor property, because this equation is set equal to 0, you set each term equal to 0. You'll notice our GCF, it didn't have a variable, so there is no x to solve for like we saw in the previous problem. But as I set 2x minus 1 equal to 0, add the 1 over, divide by 2, I get x as a half. When I set x plus 1 equal to 0, subtract the 1 over, I get x equals negative 1. Again, using the first derivative test, where when I'm not given an interval, I go from negative infinity to positive infinity, putting my critical numbers in numeric order on this number line, I then can drop those critical numbers, and in my case, my endpoints, into different intervals. I am going to test a point in the first derivative from each region. Negative 2 is in the first region, I said from each. 0 is in my middle region, and positive 1 is in my last region. If I plug negative 2 into 6, there's nowhere to plug it, so it's positive. Negative 2 here will give me negative 4 minus 1. It's going to be negative, and negative 2 plus 1 is still negative, and this is going to multiply to a positive, so I have an increasing region. Plugging 0 in, it just wipes this out, so I'm going to have a 6, a negative 1, and a positive 1, which multiplies to be a negative, so I have a decreasing region. And plugging positive 1 in doesn't do anything for the 6. 2 minus 1 will now be positive, and 1 plus 1 is positive. 3 positives multiply to a positive, so I have an increasing region. We said whenever we go from increasing up to decreasing down, I have a maximum at that critical point where they change, and from decreasing down to increasing up, I have a minimum at that critical point. So now I've got my two critical points that I want to find the coordinates of by plugging them into the original problem. And I can go ahead and list these critical numbers. I can go ahead and talk about my intervals of increase and decrease because I have listed them in my first derivative test. My interval of decrease, my local max, and my local min. But then we're asked three more questions about concavity and inflection points. So remember, for concave up, concave down, and inflection points, I start with the second derivative. So I need to come back to this first derivative, the first derivative to take a derivative to get my 24x plus 6, and then of course we're not going to say minus 0. An inflection point is when this is equal to 0. Because I have a single x, I can just solve for it. I can subtract 6 to the other side. I can divide by 24. I can simplify, and I have an inflection point when x is negative 1/4, which is, well, you see we also plugged that into the original to get that coordinate. But here's where concave up and concave down comes in. Again, I have my inflection point, my negative and positive infinity, so I can make my intervals. And if I test a point inside each interval, -1 is in the first interval, in the second derivative, in this function, -24 plus 6 is negative. Negative numbers are pointed down. I have a concave down region. Concave down regions have maximums. If you come over here, we just said we have a maximum in this region. We also said we have a maximum at -1 when x is -1. -1 is inside that region. When I pick a number in my second concave region, 0, plug 0 into the second derivative function, I just get a 6. 6 is positive. That means it's concave up. Concave up regions have a minimum. So in this interval of -1/4 to infinity, I should have a minimum. Well, we've already stated that we have a minimum at +1/2, and that is in that interval. So just to kind of tie it all together.